of the lecture series on mountains and geologic structures. I thought I would throw this in because the first two parts didn't cover mountains well enough. So let's dig into this. Mountain belts are chains of mountains that are thousands of kilometers long. You typically don't find them in the middle of continents. You find them at the edge of continents or where plates are banging into each other. Let's take a look at that. Ah, I just love this. But only if I can get back down to the warm cocoa. Here at the edge of North America, we have the ancient Cordillera of North America. You have the Andes in South America. You have the Atlas Mountains and the Alps, where these two continents are banging together. This is the one exception to mid-continent mountains, the Himalayas, and it's only because this is the Indian plate, which is running into the Asian plate. So it looks like they're at the edge of a continent. They're not. Eventually they will be. As India plunges underneath Asia and scrapes off everything on here, this will become the edge of the continent. And then over here you have the New Zealand Alps, which are kind of an exception too, because it's just an island chain. Mountain belts are part of the geosphere. They form and grow by tectonic and volcanic processes over tens of millions of years. It's not a quick process. You don't just pop up a mountain. They change the hydrosphere because they block the flow of water, making one side more rainy, the other side more dry. Let's go back to this. This side over here tends to get really rainy. Think of the Olympic rainforest up here, and then get back into eastern Washington and Oregon here. It gets very dry. We are in the Basin and Range Desert over here. There is the desert on the backside of the Andes here. On the backside of the Himalayas, you find the Gobi Desert and Mongolia. So mountains often change the weather. Now, oops, did I just skip something? Nope, I'm good. Mountain belts tend to be longer than they are wider. Let's go back to, here. This is the North American Cordillera, and it actually is one long mountain chain that wanders down here. It's very long. Older mountain ranges, like the Appalachians, tend to be lower. Let's look at a picture of that. We have really large mountains over in this area. If you've ever been over toward Tennessee, Kentucky, Maine, New Hampshire, they have mountains, but they aren't nearly as big. I was just talking to a friend from, upstate New York. Somewhere over here, you guys. And she was very impressed with the size of our mountains. And I thought, don't you have mountains in the Appalachians? She goes, yeah, but they're not as big as this stuff. Sorry, as this stuff over here. These are old mountains that have worn down ever since they were formed. Now, really old mountains tend to be worn almost flat. Oops, got to come back to that one. This is the northwestern part of Australia. These are extremely old mountain ranges that have been worn flat. You don't hear about them in Australia because, well, they're not very big mountains. Now, oh man, I hate to do this, but I've got to readjust this. How does a typical mountain belt form? Let's take a look. Oh. I'm just here to irritate you. Here is the ancient rock of the continent. Here are plutons, molten rock that has come up, rising through the basement rock here. This is the metamorphic rock of the continent. We've talked about this before. The rocks tend to get worn down and they get stacked up in sedimentary rocks. You end up with basins and you end up with domes. Not everything's completely flat. Where the old basement rock is exposed, that's called the shield. And this for North America occurs in the eastern part of Canada. Over here in the western US, this is what's going on. All kinds of collisions. So we have materials that are getting folded and lifted up into blocks. Now, mountain belts typically contain thick sequences of folded and faulted sedimentary rocks. You would think they'd be all metamorphic and granite. Not so. They may have great thicknesses of volcanic rock. You also end up with things that are called folds and thrust. When you squish things together, you end up with shortening. And if you pull things apart under tension, you get thinning. Let's take a look. If you look carefully, folds going on. How did that happen? Continents being squished together. This had to happen deep underneath the water. By the way, this looks like water. That's the edge of a snowy slope. Don't think this is like a fjord or anything like that. What do I want to say about this? Here we go. On the western coast of North America, as the Pacific plate plunges underneath us, we end up with all kinds of stuff being kind of scraped off on us. Let's say you had a really dusty table and you scooted your hand flat across that table. What would gather along the leading fingers of your hand? All kinds of dust and crud that was left on the table. That's the same thing with Western North America. Now, as this plunges underneath us, this basement rock tends to get elongated and it stretches out and it causes normal faults. And that creates rift valleys like we see in the case of the Verde Valley or all over in Nevada. You also get all kinds of crazy activity, so you end up with batholiths and melting and occasional volcanoes like we see in northern Arizona. Back east, where you see stuff being rammed together, and we'll talk about this more later, you end up with all kinds of crazy folds like this. Now, batholiths tend to be resistant. They form granite domes, and they don't break down very quickly. Let's take a look. Here's your typical graben and your horst. Phoenix is actually located in something like this. We have fault block mountains or normal fault mountains up here. We are living down on the sedimentary rock down this way. And our aquifer is down in here. So when we farm in this area and we spray pesticides and herbicides on the crops, all those pesticides and herbicides are going down into here, into our water table, and then we pump the water back up. And we say, hey, it's no big deal. Those poisons go away. No, they don't. Everything must go somewhere. Let's make this really simple here. This is a picture of Europe. This is down toward Africa. This is up toward the North Sea. In the northern part of Europe, glaciers have just shaved everything off. But there's been all kinds of thrust faulting going on here. What's going on? Why would this rock be pushed on top of this rock? Well, Africa is running into Europe. So everything is being foreshortened or squished together. You have in here, this is kind of crazy, near the Rhone Valley, rock here that's the same as the rock there. What's happened is it's been squished up and over, and then it's been shaved off by ice. This is just kind of crazy. And a lot of the rocks in the Alps actually belong to Africa. And this gets a little complicated, so don't even pay attention to that. Pay no attention to that man behind the curtain. Okay, after a convergence stops, you get some uplift and block faulting occurring. Everything here is stopped running together, and what you get is isostatic adjustment. When the top of the mountain wears down, the bottom of the mountain bounces back up, just like taking an elephant out of a rowboat. The rowboat will bounce back up. But when this bouncing up happens, you get all kinds of faulting going on, and this is what's happening in the western part of North America all through the Rockies. Here are some old folded surfaces. Here's a pluton or intrusion. And after you've worn some of that away, you end up with normal faults, and the granite becomes a mountain peak, a very resistant mountain peak. Granite, like you see along 16th Street and the 101, is very resistant. Here are the Grand Teton Mountains in Wyoming. These are fault block mountains formed something like this. Again, this used to be the home to Glacier National Park. Well, it's still the home of Glacier National Park. It's just that Glacier National Park is missing something, and it's neither the national nor the park. Now, mountain ranges change over time. Here is what we have in the west, the Basin and Range Province. It's caused by elongation. As the Pacific Plate goes underneath us, it stretches this part of North America out, so you get all these faults going on, and this extension type of thing. And this is what you see around Phoenix and western Arizona, and then all the way up into Nevada. This kind of thing. Now, continents can grow several ways. You get igneous activity, adding lava to the edge of the continent. And when pieces go underneath North America, things are scraped off. California gets kind of crazy. What they're talking about is right here. California and British Columbia, Oregon, Washington. All kinds of things have been scraped off onto North America. It's really kind of cool if you go up there and look at it geologically. Okay, quick summary. What kind of mountain is this? It's a fault block mountain. What has caused this? This is tension, where things are being pulled apart. Here the hanging wall has moved down and the footwall has moved up. This creates some of the most beautiful mountains, I think. Here is another example of a fault block mountain. You can see this kind of thing as you head up Highway, I think it's 89 north of Flagstaff on the way to the Grand Canyon. You're heading up here to Cameron, and then you go up here to the Grand Canyon to look down in the canyon. This actually is a monocline, so I'm lying to you a little bit. But you get this kind of thing going on. This is a dome mountain. Imagine that you put a bunch of blankets down on the floor and, okay, on a table. Then you drilled a hole through the table, and then you had your hand come up through the middle of the table, and then you sawed the blankets off. This is what you get. Something underneath here, either salt or like an igneous intrusion, raised this area and created all these weird folds. This is the Dragos Mountains and the Sahara Desert area. This is what the edge of these things can look like. It's incredible folding going on. This is an anticline, which we talked about in a previous lecture. And this, some of you may recognize if you look at satellite images a lot. This is the eastern coast of North America. Take a look at an old meandering river here. I believe this is the Shenandoah. This is all farm fields in here. And these are the Appalachian Mountains. These are folds. This is where that's from. And I believe that's almost it. By the way, these are the Finger Lakes of New York. This is where glaciers from the Ice Age scraped out large areas. They melted, and these depressions are left behind. Okay, one more cool. This is Sidling Hill, I think in Maryland or somewhere like that back east. I stopped over here once, came over and took pictures. This is old sedimentary rock that has been folded into a syncline. This is just incredible. The sedimentary rock, when it gets folded, gets put under a lot of stress, a lot of pressure, so it's become metamorphosed. And a bunch of this rock was used to make pillars for the hotel in which I was staying. It's kind of weird. You would think the bottom of it would be really weak, but the bottom has been squished together. The limbs or the sides, they've been stretched out, and as they're stretched out, they become really weak, and they erode faster. People like looking at this, so they built an exhibit center over here. Okay, we have an anticline, we have a syncline, we have a dome mountain, and boys and girls, I think that's pretty much it. Thanks for watching.